Hello AP Cal class, we are going to run through the notes for section 4.3 and we are going to introduce what a definite integral is. Also going to talk a little bit about partitions of unequal width. Trapezoidal rule, that'll be in a different video, and I'm actually going to probably break this into about 3 videos. And I'll be re-recording this because I just did it the first time with the sound off, so we'll do it again. But luckily for you, I'll probably go a little faster the second time. So here we go. I'm not going to spend too much time. We've done a lot of this limit definition stuff, and so we saw this before. We're finding the limit of a sum as the number of rectangles. So n is like the number of rectangles we draw would approach infinity, and the way we do that is the function value, whatever our function is that we're finding, the rectangles under, the area under, is the height, and then b minus a over n is the width, and then this a plus b minus a over n times I f of that. That's telling us where we're evaluating the function. We have to put a plus because we don't always start at 0. So if we're starting, if our interval starts at 1 or at 10 or something, then we have to start at that point when we start evaluating. Okay. Now, as we move toward doing actually definite integrals, they're going to make this formula look a little more concise. So f of c, or f of c sub I, depending on which term we're on, they use that sub I, is going to replace all of this, and then delta x sub I is going to replace the width. Okay, so it's a little more of a concise formula there. As far as unequal widths, I'm going to jump ahead to example 1 because this is the type of question that I see on the AP exam quite a bit for basically testing your knowledge of how to deal with a function where the widths are different. And what they mean by that is, we just have some random data points here, and it doesn't just go by a constant amount every time. It goes from 2 to 3, from 3 to 5, 5 to 8, 8 to 10. So we have some different widths to deal with there. Okay, and so here it says find the area under the graph of y equals f of x above the x-axis on the interval from 2 to 10 given the following data. Now here it says using an upper sum. Okay, so we've talked about upper sums, and we did that in the context of, hey, if we're doing, let's say we're doing right side rectangles and it's an increasing function, then we got an upper sum because we do the height on the right side, and that was the higher one, right? Now here, in lower sums, it doesn't always mean that a right side is upper, but if the function's increasing, right side would be. Now in this one, our function is, it's increasing a little bit. We don't have like an equation of the function. We just have some data points, and they get higher for a while, or I'm sure looking here, they get 5 to 7 to 11, but then it drops again, right? So what the upper sum idea means is just always pick the bigger of the function value, which would be your heights. So I sketched this out. Now if you were actually answering this question on an AP exam, you probably don't want to take the time to sketch this out. I'm just doing this for demonstration to kind of show you what it is that we're really finding here. And so I just plotted these points. So I got 2, 5 here. This is 3, 7. This point here is 5, 11. And then we've got 8, 10, and 10, 6. Okay, so upper sum, my width is going to be, the distance between the x-coordinates. We're starting at 2. We're not doing anything back here. Our data doesn't start until here. So we're going from 2 to 3. And between 2 and 3, at 2 we have a height of 5, and at 3 we have a height of 7. Upper sum means take the bigger of the two. So when I draw my rectangle, I'd be looking at this one right here, the one that has the height of 7. So the area of this first rectangle, width of 1, height of 7, would have an area of 7. Okay, then as I move to my next one, from 3 to 5, I've got a width of 2 there, and I've got 2 heights to choose from. I want to choose the bigger one, the 11, and not the 7. So I've got the height of 11, and then the width of 2. So that's going to give me an area on this rectangle of 22. Okay, and moving to the third rectangle from 5 to 8, there I've got a width of 3, and I'm choosing between 10 and 11. I want to pick 11. That gives me the bigger one, so I keep that same height of 11. And so I've got 11 times 3. That would be a width, or I'm sorry, an area of 33. And finally, for my fourth rectangle, because we're doing n equals 4 rectangles, my fourth rectangle between 8 and 10, so it's a width of 2. I'm going to take the bigger height of 10, so that's going to be 2 times 10. I should have 20 right there. Okay, so I'm going to add 7 plus 22, it's 29, and then 33, it's 53, that should be 82, so I'm going to get 82 for my value there. That would be my area. Area is 82, and that's using the upper sum idea. So the idea, we're just taking the bigger of the two. Now, like I said, if you came across a problem like this on your exam, probably don't want to take the time to draw this out, so you're just going to grab numbers off the chart, and you're going to say, okay, my width here is 1, and I need to pick the bigger of the two. I'm going to pick 7. So 1 times 7 plus. And I'm going to go here. I'm going to say, okay, this width is 2, and I need to pick out of 7 and 11. Okay, I'm going to pick the 11 for that. So 2 times 11. And then from here to here, I've got a width of 3. And I need to pick between 11 and 10. I'm going to pick 11 again. So I'd have 3 times 11. And then last one, I'd go, okay, here I've got a width of 2. I need to pick between 10 and 6. And so I'd pick the 10. So I'd go 2 times 10, and then I just total those up, which would give me what I have right here. But this is kind of a visual of really what we, the shape that we were finding the area of, okay? But like I said, for saving time, you'd probably do it like this. Now, they don't always say upper sum either. They might say just always use a right-hand rectangle, okay? And if that were the case, I would have, if they said that, then I would have always picked, between the widths, I'd always pick the one on the right. So it would have been 7 here. And then on the next one, I would have picked the 11. And then on the next one, I would have picked the 10 and then the 6. I would have just omitted the 5, right? If it's at a left-hand rectangle sums, then I would have started with the 5, and I would have ended at the 10, and I wouldn't have used the 6 at all, okay? So in a problem like this, they'll always say, number of rectangles is going to be 1 less than the number of data points you have, because, you only have that many widths in between, right? If you have 5 data points, you've got 4 widths in between, so that's the way they'd give you that information. Okay. Next thing, okay. I do run through one more limit definition here, and we'll talk through it fairly quickly because I think we've done enough of these from the last section. So just to tie these concepts together, it says it's no accident that the symbol for summation, which is sigma, eventually evolved into, this is our integration symbol. We're going to see this a lot now. So after all, they're both similar to the Roman letter S, which is what the word sum begins with. Therefore, calculus has a new way of asking a familiar question. So we're going to start saying this symbol rather than this one. Okay, so one more time, it says evaluate the following definite integral using the limit definition. So if our function is just 2x here, and our interval goes from -2 to 1, right? So that means that our width, from -2 to 1 is 3, and so it's b minus a over n, so it's going to be 3 over n. I'm going to be using that for the width. And then f of 3, 3 over ni, and then we also have to add a. We started at -2, so that's why I have the -2 plus that in there. And so substituting f of, so we're plugging in there for x, so it's 2 times this, right, because I'm doing f of that expression. And then we gotta simplify all this stuff up. So to add these together, I'd get like get a common, it's going to be 2 times -2, which is 4, -4, I should say. And then I get a common denominator of n, so I'm going to say it's -4n over n, and then I can add that to, then this 2 gets distributed, so I have a 6i over n there. Okay, so that's that expression. Now this n on the bottom, since I've got all that as one fraction, I can kind of pull that out here, and that's why that becomes n squared. And then I'm looking to, do the sum of each of those terms individually. So I'm writing those out individually, and because there's no I in this one, I'm just going to take that -4n, I'm going to bring that out, and then I just have the constant of 1 there. With this one, I've got the 6i, so I'm going to take the 6 out, and then I'm going to substitute the summation formula for I, which was n times n plus 1 over 2, okay? And then I'm going to, this right here, this summation of a constant, remember, summation of a constant is just the constant times n. Since my constant here is 1, then I'm just going to have, that's just be n. So n times the -4n out there becomes -4n squared. And, okay, so I've substituted the I formula here. Now, I did omit some of this work because I did refer to this in some other videos, that the leading term is really the only one that's going to affect our answer at all. So even though there's only one other term, I would have had like a plus 6n after this, but that's just going to disappear when I do my limit as n approaches infinity, because that's still going to have an n in the bottom. So I only concern myself with the highest degree terms, which in this example is n squared. And so I'm going to be dividing by this n squared here as well. So combining these together, I end up with -2n squared over 2, and then times my 3 over n squared right there. And then as I simplify that, I end up with -3n squared over n squared. So that limit just simplifies down to -3, okay? So going through that limit definition here, I get -3 for the value there. Now, if we're going to talk about how that ties into where we're moving now. It says, okay, so it says, what do you notice that's unusual about this answer? I don't think we've had one that's negative before, so I think that's maybe what's a little unusual about it. But I do want to try to help you understand why it turns out to be negative in a geometric sense. So this function, 2x, if we were to graph it from -2 to 1, it's just a line with a slope of 2 and a y-intercept of 0. But so this part of the line is going to be below the x-axis, right? So from -2 to 0, we've got this part of the line that's below the x-axis. Now, we're going to talk about, these definite integrals in terms of geometrical area, okay? Now, some of that area is below the x-axis, some of it's above the x-axis. Now, the area of a triangle is just 1/2 base times height. Base on this triangle, 2, and height being 4 times half, so this would be like a 4. However, in terms of its definite integral value, if your area is below the x-axis, we give it a negative definite integral value, even though areas are always positive. But as far as the definite integral, you can have a negative value for that. So it's represented as below the x-axis when it's a negative definite integral value. And then this part here, which would be 1 times 2 times half for the area, that's just 1. So when I combine those together, I get a -3. -4 plus 1 would be -3. So geometrically, that's how that comes out. Okay, I'm going to do examples 3 and 4 in this video, and then we'll do another video for the next middle piece of this. Okay, so these ones are asking us to set up a definite integral that would calculate the area of each region below. So what we're trying to find is the function that's kind of enclosing this area. Now, as far as the vertical pieces, that's just going to be, where do I start and where do I end? Those are going to be the bounds that I have, on the top and bottom of my integration symbol. So I'm starting at 0, and I'm finishing on this one at 5. So I would go 0 to 5. And then the line is just a horizontal line, which is it's just a constant. Okay, and where is that? It's up at 3, so it's just the line y equals 3 or f of x equals 3. So it's a real simple one. So now the one other thing that I put in here, okay, so this is my function height is 3. Now remember, we were always doing height times width, right? And what we were using before was b minus a over n for that width. But what we're going to kind of translate that into, and they kind of referred to that up here. I want to point this out again. So instead of this now, we're going to call it delta x, which is our small change in x, okay, delta x. And then it actually, delta x kind of moves into dx, okay? That means delta x, okay? And so we're going to use delta x dx on this one, okay? And that's what you'll see. And if you recall from when we did our implicit differentiation, we were saying like dy dx at the end of different things. It's going to be a similar notation, and we'll see when we start solving some differential equations that it makes sense for the dx to be on there. But think of it as like delta x, or the change in x. It's the width of your infinitely thin rectangles that are under there. Okay. All right, next function here. So here we see like basically 2 line segments, and we could write it in 2 separate integrals. I do want to point out so that we can recognize these. Whenever you see like this kind of V shape or upside down V shape, you should be thinking in your head that this is like an absolute value of x type of graph. But because it's opening downward, that means that it has to be negative. There has to be a negative in front of that. And the vertex is shifted up 4. Okay, so since that vertex is shifted up 4, I want to put a +4 at the end of this. Okay, so I will have, for my function, now if I do this all in one instead of breaking it into 2 different lines, I would say I'm going from, I think it's -4 to +4. And then, like I said, it's an absolute value, but it's negative in front of that because it's inverted. So I put the negative out in front of that, which flips it upside down. And then it's also shifted up 4. Okay, so this would be my expression right here. And so that would be this graph. So it's just going from -4 to 4. We'd see that exact shape. Okay, so that's how we would set that up. Now, if you were doing this analytically instead of geometrically, and you're like working it out, which we're going to move toward that, where we actually have formulas to integrate with, it would probably be easier to break this into the 2 different lines that instead of having to use a formula for how do I integrate absolute value. I would probably just go, okay, I'm going to go from the integral from -4 to 0. So I read them from left to right. I'm going to go from negative, that's important when you do these, -4 to 0, left to right. And that line is this one, which has a slope of 1 and a y-intercept of 4, which should just be then x plus 4. And the other piece of it right here has a negative slope, so it's a slope of -1, but still a y-intercept of 4. And my bound for that starts at 0 and ends at +4, starting here at 0 and goes to +4. But like I said, this one would have the negative slope, but still a y-intercept of 4. And then again, I'm going to put, it's dx. So this is my function, which represents the heights of your rectangles in there. The dx is your width. So you always put a dx at the end of that when you integrate something, when you write your definite integral. Okay, so that's how we can, two different ways we could set this one up. Probably this is what you would see for right now, but as we start evaluating them analytically, you'll probably break it down to that. Okay, we just got, I think, 3 more before I stop video for this one. Okay, this one asks us to sketch and shade the region whose area is given by the definite integral, and you can use geometry to find the area. Okay, so for this, we've just got a line 2x plus 5, so a y-intercept of 5, put that up here, and then a slope of 2, so down 2 over 1, down 2 over 1. And I'm actually going to stop there because that was our, from -2 to 0, so from -2 to 0, I'm just doing that. That's basically the line segment that I get. Okay, and so then I'm looking for, when we evaluate this, we go to the, it's always bounded down to the x-axis, okay? So we go to the x-axis, and so that kind of gives me, it's almost a triangle, but it's actually technically like a trapezoid because we have this piece here. So probably what you want to do to calculate this area is just area of the triangle on top, and then I think I'd just add these 2 units. It's just a rectangle of area 2 on the bottom if we broke it into 2 pieces there. So my area would be 1/2 base times height, and the base being 2, and then the height would be 4 because I'm starting up 1, so I have a height of 4 there. And then I would just add the area of that rectangle, which is 2 times 1. I say 2 times 1, I guess. And so that's going to be 4 plus 2. Okay, and so the area should be 6. And when I say area, I mean it is the area, but it's also the value of this definite integral. It is that area. So if I say area, I'm also meaning the value of the definite integral. Okay, and that's what we're using. Area given by the definite integral there. Okay, part B. I don't know if you recognize what this equation is. It's got a square root over a perfect square minus x squared. When you've seen formulas of circles before, they were usually in the form x squared plus y squared equals radius squared. But if you solved for y or for f of x, you would get y equals the square root of r squared minus x squared. And that's basically the form that this is in. Now, technically, when you took that square root, it would be plus or minus in front of this thing, which would give you the top half of the circle, and then the minus would give you the bottom half of the circle. And, because that wouldn't be a function because it would fail the vertical line test. And then it's just asking for the top half because it's just the positive version of this. It's not saying plus and minus, okay? So we're just doing a semicircle. Okay, so we're going from -3 to +3. And we know with this, the radius squared would be 9, which means the radius is 3 of this circle. So we would just have, if we're going to sketch it, you just probably put these 3 dots on here. Try to sketch a semicircle enclosed with those 3 dots. Okay, so basically we're just finding the area of this semicircle. So circle is pi r squared, semicircle would be 1/2 pi r squared. And so with this one, we'd have 1/2 pi times radius squared, so 9/2 pi. That would be my area and also my value of this definite integral. Okay. And, okay, this will be the last example I do for these notes here. So similar, they didn't give us this equation up top, but we had the graph of it. So we're going to have a graph something like this here. And now with this example, I don't like the graph paper they've given us because they make it confusing. Just to look closely here, they're counting by 1/2 because 1 is 2 marks down the road there, and the same here. So I want you just to pay attention to that. But so again, we do have the negative in front of the absolute value, which means it's a V shape that's upside down, and then a 1 first, so that's shifted up 1. So 1 being up here. And then a slope of +1 and -1 is basically just going to give us this triangle right there. So we want to find the area under this, under this triangle right here. Okay, so to do that, it looks like we have, from -1 to +1, that's a base of 2, and then the height is just 1. Okay, so area, let's go back to my pen. Area would equal 1/2 base times height, and so that's 1/2, base being 2, height is 1. We just get a value of 1 for this one. Okay, and I think that's all I'm going to do right now for this video. We'll move on with the next examples in another video.